in the Netherlands. Our main business is our product Supertest, which is a compiler test and validation suite for C and C++. But upon that, we also provide services to validate compilers for our customers, for example. And we also work on library testing, so the C and C++ standard library. We have customers worldwide, so it's very nice to see that even though we are from quite a small country, we help customers all over the world to test their compilers, including in India. So what I will talk about today is I will start with a short introduction on Supertest and how Supertest is designed. Then I will talk about functional safety for compilers. So I will show you compilers from the functional safety perspective. I will demonstrate some examples of compiler errors. I will talk about what to do when you find a compiler error, again from the functional safety perspective. Then I will talk about testing of compiler optimizations, which is quite a bit different. And finally, I will demonstrate some examples of compiler optimization errors. So let's start with a short history of C and C++ and where Supertest fits in. So the first implementation of C is from 1972, with the first book about C coming out in 1978. That was the KNRC book. The first implementation of C++ is from 1985. So all these languages, they are already quite old. Similarly, Supertest is already quite old. So Supertest dates from 1984, or at least the first test. And that's because Supertest used to be part of a compiler development company where Supertest was used to validate those compilers. So Supertest was really developed hand in hand with compiler development as well. Later on, C really got standardized. So there were ISO standards coming out for the C language, and later on also for C++, with the first version in 1989, which a year later was also standardized as ISO C90. Over the years, quite some revisions have come out. So now we are already at C18, and this year C++20 is coming out. And well, over the years, of course, Supertest has been maintained to track those changes as well. So even though Solid Sense only dates from 2014, the product is already quite a bit older because it used to be part of the compiler development company in Amsterdam. Let's discuss some characteristics that make compilers very well testable. Well, since the ISO standards have come out for C, there's a very clear specification. So first there was the KNRC book, but that was not that clear. But now there's this ISO standard. There's really a clear document that describes all the requirements of the compiler. And based on that, we can develop Supertest to validate those requirements. Also, compilers take single input and single output. So you put a source file or a translation unit in, and without any other interaction, an output comes out, which is the object file. Usually, compilers are deterministic as well. So that's, of course, very important when testing a compiler. And finally, compilers are command line scriptable, which means that using a test suite like Supertest, you can automatically feed it a lot of files, automatically validate whether the output is correct, without a lot of user interaction. So fundamentally, Supertest looks like this. On one hand, we have the collection of handwritten tests. So those are the tests that are really written based on what we read in the ISO standards. So if there's a requirement that a certain code construct should behave like this, we have one or multiple tests that validate whether that behavior is being implemented by the compiler. On the other hand, we also have diagnostic tests. So those are the red crosses over here. And the red crosses indicate the diagnostic test. So that is if the ISO specification defines a constraint of the language. So for example, you should not do this. Then we write a test that violates that constraint. And then we validate whether the compiler provides an error and does not incorrectly compile the program, even though it is a wrong program. On the other hand, we have a very big collection of generated tests. These tests are, for example, specifically generated for a specific data model. So then we do arithmetic testing, or for the calling conventions, that kind of testing. And well, for those, we don't need to do handwritten tests because we can just write one or multiple templates and then generate tests based on specific properties like a data model. All these tests, they are driven by our test driver. So the test driver automatically feeds programs to the compiler, then validates the output, and our test reporter shows an overview of the results, so which tests are passed and which tests are failed. And this all fits in quite nicely into the V model of software engineering. So there are three different layers. The bottom layer is unit testing, and that really focuses on the implementation of the compiler. So for example, for LLVM, that would be the LLVM test suite. And those tests are really developed based on what Clang looks like or LLVM looks like from the inside. And also those tests, for example, only target a specific compilation option or a specific optimization. And so those tests are really developed with knowledge of the compiler internals. One layer on top of that, there's testing according to the specification, and that is where supertest fits in. So there we test the compiler really based on what has been specified in the document, the requirements document, and then we validate whether those requirements are correctly implemented by the compiler. On top of that, there's also validation, and that's more about the usability of the compiler. So for example, whether the user is happy with the optimization performance or the speed of the compiler or the usability of the compiler. And that does not really have to do with the correctness of the compiler. Now, this is an example of how the language is specified. So this is an example from the ISO C90 standard. And this discusses the comma operator. So on top, there's the syntax of the comma operator, which shows that, okay, it is we have an expression, and that expression can be followed by a comma and then followed by another assignment expression. And since this expression is recursive, you can have multiple comma expressions in a row. More importantly are the semantics, and those require that first the left operand is evaluated, then there's a sequence point after the evaluation, and then the right-hand side is evaluated. And the result of the right-hand side is the result that will be, for example, assigned to the variable, or that will be returned when you have a comma operator in the return statement. So a test in supertest for the comma operator looks like this. So that's based on the specification that we just read. Here we have the test function where we define an integer a, an integer pointer p, and another integer r, which will store the result. Then we set p to be the address of a, so p becomes an alias of a. And then here we have the comma expression that we will be testing. So first we feed p to this function here, which sets the value of p to 2, which means that now also a is set to 2. Then in the next expression, we increment a, so a becomes 3. Then we add 3, so it becomes 6. Then we add 8, so it becomes 14. And in the end, we have an expression a plus 8, which will be evaluated and should evaluate to 22. And since in the semantics they stated the right-hand side should be assigned to the expression value in the end, here we validate whether indeed the value of r is been set to 22. Now, if that's the case, then the compiler correctly implements the semantics. Similarly, like I said, we also do diagnostic testing. So here we have the specification of the logical AND operator. And there a constraint is defined which says that each of the operands of the AND operator should have scalar type. So both sides should be a scalar type. And according to that, we can develop a test like this, where we have the AND operator here. On the left-hand side, we have I, which is an integer, so that is scalar type. But on the right-hand side, we have X, so an X is a structure, so that is not a scalar type. And then we validate whether the compiler indeed produces an error, which in this case, with Clang is the case. So it says there's an invalid operand to the binary expression. And then again, we validate whether the constraints is correctly implemented by the compiler. So let's now look at compilers from the functional safety perspective and why there's such a big safety impact for compilers in terms of functional safety. So if we would, for example, be developing code for the braking system of a car, that code goes into the compiler, the program comes out, and the program is what ends up in the car, not the code itself, of course. So now if you have fully tested your code, you've proven your code to be fully correct, there is still a chance that when you feed it into the compiler and it comes out of the compiler introduces an error, and that could lead to a safety hazard. Now, of course, if you were developing a simple website or an application, you might be safe to just assume that the compiler is doing the right thing. And if something goes wrong, yeah, there's not really a big problem. Maybe you find a bug or a user will report a bug to you, but there will nobody will be harmed. But in terms of cars, of course, even the smallest risk of the compiler being incorrect is a risk that you cannot take because, well, maybe this will happen. But luckily, taking a risk like that, that's not allowed. So in the functional safety area, there are very strict safety standards for software. And they also talk about software tools. So in terms of the automotive industry, there's the ISO 26262 standard. And that tells the developer to create confidence in the use of the software tools that they use. And of course, the compiler is a tool like that. So the goal here is to develop confidence in the compiler. And one of the recommended ways to do that is by verifying it against the language specification. So by verifying it against the requirements of the compiler. And of course, Supertest is a tool that is able to do that. If you get the results, there might be some compiler failures. And of course, as a LLVM developer, you would just dive into the compiler, fix it, and then rebuild the compiler and use it again. But from for an automotive developer, that is very different because they often don't even have access to the compiler. They pay a lot of money for the compiler, and new versions might not come out or might never come out because it also happens that legacy compilers are being used in this area. Because projects, of course, they take years and years, and when finally the project is done, the compiler might already be a legacy compiler. So instead of fixing the compiler, what is done in the automotive industry is documenting the compiler failures and defining mitigations for those failures. So that means that there will be defined a way to make sure that that compiler failure will not end up in the application, so that there is no risk of that error breaking something in the application. And all of this is very important to do for the specific use case of the compiler. So that is, for example, the specific set of compilation options. Because, of course, a compilation option might change something in the behavior of the compiler. So using a certain option might fix or break a specific compiler error. And if you don't create confidence in the compiler for the exact use case that you are using to compile the end application, well, then you still don't know how good or how bad the compiler performs. Now, all of this is quite an established practice for the automotive industry, but also for other functional safety industries like the railway or the robotic world. But then there are different safety standards, but all of them quite similarly define that tools should be validated to get confidence in them. So over the years, we have seen that actually every compiler does have some errors, but it is really different how bad those errors are. So there are different levels of compiler errors. On one hand, there are compile time errors. So that, for example, means that you compile a program that is correct syntactically, but the compiler does not understand it. Maybe the compiler crashes. And of course, as a LLVM developer, you don't like to see a compiler crashing and you would like to fix that. But in terms of functional safety, that is not really an issue, because if the compiler crashes, no incorrect program is being produced. So no incorrect program can end up in the car, for example. So there's no real safety risk related here. Similarly, there are diagnostic errors, and those are a bit more serious. So that means that if there is a constraint violated of the language, so you do something that according to the language specification is not allowed, but the compiler does not detect that, then still the compiler produces a program, but the program does not have any meaning according to the language specification. So then you have a safety issue because, well, you compile something that has no meaning. So what will the program do? Also, serious errors are runtime errors. So that means that you compile a program that is correct, but when you execute it, the runtime behavior is incorrect. So the compiler incorrectly compiled the program. And then there are two different levels. So you have mitigatable runtime errors, which are the runtime errors that there is a way to work around. And on the other hand, there are really bad runtime errors, which means that, well, there's not really a way to work around them. And then the compiler is simply unsafe to be used. And in the coming slides, I will show an example for each of those errors. So this is a compile time crash in LLVM 3.9. And what happened here was we have a function which is defined constant expression, which has a nested clause here. And the constructor is also defined constant expression. But here the value of x is used, which is a diagnostic or a constraint violation. So we developed this test because we expected the compiler to produce a diagnostic. Instead, by compiling this in LLVM 3.9, so it's quite old already, the compiler just crashed. And in terms of functional safety, like I said, this is no real issue because no program is being outputted by the compiler. So no wrong program can end up in the car. Then here we have a diagnostic error for GCC and LLVM, which is caused by a GNU extension. What happened here is we have here the conditional operator, which here takes the condition tree. Usually here after the question mark, that would be the expression that will be evaluated when the condition evaluates to true. And then after the colon, there's the false expression. Now what happened here is the true expression is being omitted. And syntactically, according to the language specification, this is an incorrect program now. However, a GNU extension allows you to do this. And then the meaning of this will be that if the condition is true, the condition will be evaluated. So here the function would return 3. The problem here is, in terms of functional safety, that there is no clear specification of what is the behavior of this code construct. So, for example, if you by accident forget to write down the true expression, well, then suddenly the behavior of the program can become different than what you expect. And then again, there's a functional safety issue because, well, the standard requires to give a diagnostic here instead of compiling the program. And of course, this program is compiled, so it can end up in the car. So that's a safety issue again. Then this is a runtime error that is present in GCC, also in the latest version. And what happens here is that we have two structures. One is the contact structure, which contains a phone number and a fax number. And the second structure is a house, which contains the address, which is also a number, and which contains a contact, which is this structure here. Now we initialize the contact by setting the phone number and the fax number. And we initialize the house by first setting the address to 501, then setting the contact to the contact that we initialized here. But then we also override the phone number of that contact. So after doing this, we would expect to get a phone number of 650 in the home contact and a fax number of 999. But instead, the fax number is being set to 0. So in terms of functional safety, here there is an issue because the runtime behavior is incorrect, and of course that is dangerous again. Now to mitigate this, we could, for example, just say that we should not use this way of initializing a structure by partially overriding another structure, because this issue is very clearly related to a specific syntactical feature. So by just saying that you should not use that feature, then the risk is being mitigated. And finally, this is an example of a really bad runtime error. And that is one we found in an embedded compiler of one of our customers. What happened here was we have an array S for which we set the first value to 42. Then there's SP, which is an alias of S. So if we set this SP0 to -1, we would expect that S0 will also be set to -1. Instead, when we evaluate S0 after doing this, it still returns 42. And this is a really bad issue, of course, because first of all, the compiler did not specify any optimization flag. So we did not ask the compiler to optimize the code. And even worse, there was no option to turn this optimization off. So whatever you did, however you use the compiler, this issue was always present. And another issue here is that it is not linked to a specific syntactical feature. The compiler simply fails to do the alias analysis correctly. So there was also no real way to work around this, because it is not a clear syntactical feature that is going wrong. It is just the compiler optimization that is going wrong. So in the end, we concluded that this compiler was simply not safe to be used in a functional safety project. So this issue was related to optimizations, and so far we have only talked about the language specification. However, optimizations are not mentioned in the language specification because they are non-functional requirements. So the language specification only requires that the behavior of the program that the compiler produces is correct, but it does not care about how that behavior is being achieved. So the compiler is free to optimize the code as long as the behavior of the code is correct. And of course, then you can get a lot of performance improvements, so that is a very valuable feature. However, a problem here is that, or a problem, at least a safety risk, is that compiler optimizations, they change the code that you write. So they might remove a piece of your code, they might unroll a loop, they might copy certain parts of your loop to specialize it for a certain iteration count, etc. And now, of course, how do you know that the compiler is doing that correctly? All software contains bugs, so yeah, also the compiler optimization might, of course, contain bugs. And that is why we have worked on a specific test suite for this, which I will talk about later. So a small experiment here already demonstrates the performance improvements thanks to compiler optimizations. So here we have a for loop that iterates n times. Each iteration, it adds a value to the total, and in the end, the total is returned. Now, if we run this loop 1,000,000 times at an input of 999, at O0, it takes 2.7 seconds, and at O fast, it only takes 0.16 seconds. So that is an improvement of about 15 times. And especially, for example, in the automotive world, that is very valuable because the hardware can be smaller, the batteries can be smaller, because they're simply better performance. So you can use for maybe cheaper hardware to achieve the same performance as you would achieve with faster hardware, but then without optimizations enabled. However, like I said, still we don't know whether the optimizations are correct. And therefore, in safety critical applications, it is quite common to use a compiler without optimizations at all, because it's simply too risky to use compiler optimizations if you're not sure whether the compiler is doing the right thing. So that is why we dove into investigating how we can design proper tests for optimizations. And let me illustrate why that is so important first. Well, out of the box, benchmarks is not a good idea to look into compiler optimization testing, because they often only care about performance. So they test how good the compiler is at making a program faster, for example, but often they do not verify whether the result of the program is still correct. Also, benchmarks can have undefined behavior, especially for different data models. So if you have a smaller integer size, for example, you might run into integer overflow inside the benchmark. And finally, benchmarks do not execute all of the generated code. And that is what I will demonstrate now. So here again, we have the loop that we just discussed. If we would write a test for this loop based on the source code, We could, for example, take an input of n is 999, because then every single line of the code is being executed. And also this branch condition here, I smaller than 0, is taken in both directions. And if we compile this without optimizations enabled, we also achieve full assembly code coverage. So every instruction that is produced by the compiler is then being executed. And that is illustrated by the plus sign next to the instruction. However, if we now enable compiler optimizations, well, first of all, of course, we see that the code explodes in size. So that is the rewriting of the code that I was talking about. So the loop is being copied in different scenarios. But the problem here is that now for the same unit test that we selected based on the source code, not all the assembly code is being executed. So all these red instructions here with a minus left to it, they are not being executed. All these branch instructions in blue and pink, they are only taken in one direction instead of both directions. And what's also interesting is that these pink instructions here, those branches cannot even be taken in two directions because they are redundant. So they could just be replaced by a regular jump instruction, because this condition can never be met. So now to fully test this piece of assembly code, we would need 5 different test inputs. But the problem is that based on the source code of the program, you do not know which inputs you need, because based on the source code, you think, oh, I have now 1 test input and I fully test the program, so I'm safe. But when enabling the compiler optimizations, well, that's clearly not the case. So that is why we developed the supertest optimization test suite. And there we really focused on achieving maximal code and branch coverage on the assembly code level for 3 different compiler families. So we investigated the behavior of GCC, LLVM, and the Intel C compiler. And all of this, like I said, it's based on typical optimizations and combinations of that. So on one hand, it is based on benchmarks. But on the other hand, we also studied literature about compiler optimizations, and based on that, we developed different tests. And then for all these loops, we investigated the behavior, and based on that, we selected a very broad range of test inputs that make sure that all of the generated assembly code is being executed when we test the loop. Upon that, we compute a verifiable result, so we can then verify whether the optimization is correct and not only faster. And we made sure to make all these tests free of undefined behavior. So the test suite is a generic test suite that can be used for different compilers and with different data models. So let's look at some examples of compiler optimization errors that we found using our supertest optimization test suite. This is an error we found in the Intel C compiler. And here we are looping very close to integer limits. So we start at the smallest possible integer value, and we iterate until the smallest possible integer value plus n. And if we would execute this loop with optimizations enabled in the Intel C compiler, at runtime, a segmentation fault would happen when executing this loop. And what was the issue here is that internally the compiler is calculating the range of the loop to potentially optimize it. But because we are using such small values, internally in the compiler, the calculations overflowed. And therefore, a very big value was used to access the memory inside this loop. And that resulted in the segmentation fault when executing the loop. So even though, of course, this is quite an exotic loop when looping so close to integer limits, still it shows that, well, internally in the compiler, something can go wrong. And of course, this can be a safety issue when you're looping and you don't know that you're looping so close to integer limits. Something might go wrong. Now let's look at a bit more exciting optimization error that we found in an embedded ARM compiler. Here again, we are looping this time 5 times. As an input, we use integer pointer A and integer pointer B. And for each iteration, we check whether the value of A is smaller or equal to 0. And if that's the case, we set A to 0. If that's not the case, we copy the value from B to A. Now, if we execute this without optimizations, the behavior is of course correct. So for the first value of A is 0, so that is still set to 0. The other values of A are not 0, so then the values of B are copied. And that results in 0, 2, 3, 4, 5 being in A after executing the loop. However, if we now enable compiler optimizations in this compiler, the result is completely different and also completely wrong. So now instead of 0, 2, 3, 4, 5, the result is 0, 0, 2, 0, 4. So the values 2 and 4, they are simply not changed. They were already in A. And the other values are set to 0. So of course, it's a really bad error because this compiler optimization completely changes the behavior of the code and it simply corrupts your data. So it is clearly not safe to use the optimizations in this compiler. And last but not least, since we are in the LLVM group, of course, I should also show an error in the Clang compiler. And that is for this loop here. This error is still present in the latest version of Clang. And what happens here is that we now take 3 integer pointers. We loop 63 times. And at the start of the loop, we store the value of C inside the temporary T. Then in the nested loop, we subtract every value that is in B from T. And then in the end, the value of T is being assigned to A. And now we run this loop, but not with just regular 3 different arrays. Instead, we pass, as first array, we pass A. As a second array, we pass the second address of A. So that now means that there's a data dependency between this subtraction, because B is an alias of A plus 1 index. And because here we change the value of A, after each loop iteration, there is a data dependency now. Now, if we execute this at 0 and we have input 1, 1, 1, 1, 1, and we run it, as expected, the first iterations, they are set to 64, but the last iterations are getting bigger very quickly because there's this data dependency, and each time the values that are in here are getting quite a lot bigger, so the subtractions are also changing. Now, if we run this with optimizations enabled, that this data dependency is not visible, apparently. So the Clang compiler did something wrong in the alias analysis, and it did not realize that the value of B is being changed by this value of A. So now the result is every iteration 64 instead of the quickly incrementing values inside the A. Again, of course, this is a really bad error because this corrupts the data in the array, and well, it simply breaks the code. So to conclude, no compiler is perfect, not even LLVM compilers. And in safety critical applications, it is very important to know where are the weak points of the compiler, because there should not be any risk that the compiler breaks something, for example, in a car. Therefore, supertest is not only useful for compiler developers to make sure that the compiler is doing the right thing, but also for compiler users, so they can safely use a compiler they are working with. Now, if you're interested, there's a supertest demo available at solidsense.nl. And in India, we also have a distributor, which is Meteonic. So if you're interested to get more information about supertest, you can contact them. That concludes my presentation. So if there are any questions, then I think now is the time to ask them.
Maybe we can start with a question that Fahad all already asked on the chat. Fahad, would you like to ask that question?
Yeah, that's okay. Well, can you repeat the question?
Yes, I can repeat the question. So the
Now audible? So I wanted to ask,
yeah.
at the beginning of the session, you said that
I don't know if my connection is bad, but I cannot hear the question.
Maybe I can ask that on his behalf. So
Okay.
Fahad was asking how tests are being generated using specification in the documentation. Is there some formal automation for test generation from documentations, or is it require manual effort? Are some formal languages used to convert the requirement specification into some formal language, maybe for efficient verification? I guess these are two questions. So the first question is that do you use some formal automation for test generation from directly from the specs, or does it require manual effort all the time? Yeah.
Yes, it mostly requires manual effort because often, well, it's just written text. So as a person, you should interpret what is the meaning of that. And it also often happens that there is even a discussion between people about what exactly is the meaning. So sometimes it can be ambiguous what the specification is saying. So yeah, automating it is not really possible. There are no nice formal rules that can be converted into code. It's really about interpretation of what a person reads in the document. So that is why in the presentation I showed that a lot of our tests are really handwritten tests.
Mm-hmm. I guess you answered the second question as well, but for the record, I'll just ask that are there some formal languages that are available that are able to represent the language specification?
Uh, yeah, it might be possible that, of course, there's being research being done into
Mm-hmm.
formalizing those kind of rules. But for C or C++, there's no such rules available, unfortunately.
Okay. Uh, so we are sort of in a question answer session. If you have any question, you can like unmute yourself and ask. Okay, I'll take this as that there are no questions. Uh, so there's a question on chat again. The question is, okay, pharmacy specification language does not suit you. Is pharmacy specification language good for your use case?
I'm not the most aware of
Uh,
pharmacy, but I think pharmacy also focuses on undefined behavior, but not
mm-hmm.
specifically on the correctness of the code. So what we do is we really test whether a compiler is doing the right thing. And I think pharmacy is more looking at the C code that you write, and that is quite a bit different from the compiler itself.
Okay. So, do we have any other question? Maybe on chat, or maybe someone want to unmute and ask. Oh, there's a question coming from Pradeep. Yeah.
Yeah, hi. I have a question regarding platform dependency. So if you want to run your compiler across different platforms, so how do you test that?
Yeah, so what we do is we really focus on the C and C++ specification, and those are the requirements on the compiler. And then the test suite can be used with any compiler for any platform. And how we do that is our tests, they are self-checking. So our tests, we compile them, then you run them on the platform, and then we retrieve the results from the platform, from the execution, and then we verify whether those results are correct. So that way it is all just C code, but C code that verifies the behavior of the code.
So you said that it's going to run on automobiles also. Do you have platforms that you actually run this tests and verify it?
Of course, internally as our QA, QC, of course, we do run our tests, but a lot more of our customers are testing it on very many different kind of platforms, and those are the platforms that they are using. And of course, we don't have access to all of those, but that is what our customers are doing. Okay. And using our test driver, you can then configure it to run the programs on a specific platform.
Okay.
I have a question. You talked on the optimizations front. So consider you have some specific optimization which is not seen anywhere, like it's a very in-house optimization. So how would you test it if in case you don't have test beds or some idea on, you don't know the coverage? How do you do that? Is that possible using whatever the suit you have?
Yeah, so there are two answers here, I think. On one hand, of course, our test suite is very big, so it might be possible that since we are testing almost every syntactical feature, we might run into that optimization accidentally. But on the other hand, like I showed in the presentation, there's this fee model. So on the lower level, there are the unit tests. And those unit tests, they should also test that specific optimization if it is an internal optimization of the compiler. So it is more, they are more working together, I think.
But how do I assure that, let's say, the optimization is a very new optimization, like it's not in other implementations as well? Let's say LLVM comes it, LLVM has it internally, but other folks, like other compilers, won't have it. So yeah, how do I assure that it would be tested? Is there a firmness or some kind of percentage? You know, what is the? I'm just unsure on this still.
Yeah, we have quite some numbers about how many optimizations we trigger and how many of them we test, but I'm not very sure from the top of my head what those are. But of course, if it's a very new feature, yeah, we always track development, so we should just add new tests if it is really something new. And on the other hand, of course, if it is an LLVM feature, then that should also be added to the LLVM test suite.
Maybe I'll rephrase this question a bit. Say we develop an optimization which is totally unique, and we even don't want to tell you about like what is the input to this optimization, what is the output to the optimization. So then, can we expect that it will be tested?
Yeah, that's of course very different to say. Then you would have to do analysis on our test suite. I mean, our test suite is thousands of different tests. So it's very well possible that one or multiple of them trigger the optimization. But if we do not know anything about it, then yeah, it's hard to know for sure whether it will do that or not. So then it should be the analysis of the user of the test suite to make sure that is the case.
Yeah. We have another question from the chat. How are optimization bugs detected or identified?
Okay, yeah. So what we do is, on one hand, like I said, we fully cover the assembly code. So that way, we make sure that every different variation of the optimization is being executed. And then on the other hand, well, we verify if the result is correct by having a predetermined result of running the loop. And then we compare that predetermined result with the actual result of running the optimized loop. And if that is if that result of the optimized loop is different, then we know that the bug is present in the optimization.
Hey Rami, just to, I mean, I got your reply, but comparing the dumps may not be always true. There may be some cases where you could, maybe the optimization is doing a wrong transformation, but it's still yielding a correct result. There could be some such cases, right? I mean, comparing dumps and not all cases. I mean, suppose, let's say, I'll give you an example. I am running. I have written a pass, and I am not. So in the beginning, I do not enable it, and I just take the output. And in the second, in the second example, the optimization pass actually. I mean, I have written that. I mean, it tries to check for legality first. Let's say whether it is suitable for this particular loop structure. Let's say. And it says that it has rejected and it doesn't do any transformation. So it is as good as not running that pass. So if you're comparing the values where in one case where that pass was disabled, and in another case where the pass did not execute because it was not legal to transform it. So that would not be a very good case, right? I mean, you will get the correct result eventually, but you cannot say that that pass is actually safe for optimization, or it is yielding safe results.
Yeah, that's true. So what we care about mostly is the correctness of the result. So if the compiler simply does not optimize, then in terms of safety, that is not an issue. Of course, if the optimization is analyzing it incorrectly and maybe it could have optimized the code, but it doesn't, it's unfortunate because it is a performance loss, but it is not incorrect, so it's not a safety issue. And well, we mostly care about the safety of the optimization, so it can be safely used in safety critical projects.
Okay, I see. Also, another question: can we use super test to test a particular pass, or is it like series of pass? Like you had given like O1, O2 flags. So is it like a bunch of optimizations put together, or is it like, can I target for single optimization pass?
Yeah, so our test driver is very flexible. You can configure it however you want. So you can specify any compilation option that you would like to use. So yeah, it all depends on the configuration, and it's up to you.
Okay, all right, okay. Another question. Sorry about that. So you in one of your previous slides, you were mentioning about a particular test case where if the value of AI is less than 0, less than or equal to 0, then initialize or assign the value 0, or else BI value will be assigned to AI. So in that you had given like you had run like without optimizations and with optimizations, and you were comparing them, and it was yielding wrong results.
Yeah.
So is there another way you are checking the expected output? Are there any other ways apart from like just checking no optimizations?
So yeah, what we do is, of course, most of our tests, like I said, they are handwritten. So on forehand, we determine what should be the correct result of the program. And then we validate whether the actual result is equal to what we expect. So that is the way we are testing it.
Okay, so yeah, so the expected result, are you getting that only by disabling the optimizations, or you have, in addition to that, there are other ways of getting the expected result?
Yes, but it is, I mean, it is just hard-coded in our test. So we wrote the test like we expect this. So when you execute it with the optimizations enabled, at runtime, it just checks whether that value is correct. So you do not have to run it without optimizations yourself. Because of course, maybe without optimizations, the compiler is also doing something wrong. So just comparing two results is not a good approach. So that is why we really specified what is the expected behavior.
Okay, I see. All right, I think there's another question. Thanks for the response.
Yeah, thank you for your nice question.
We have 2 more questions on the chat. Oh, 3 more questions from the chat. So Fahad is asking, can ML technique be used on top of formal testing and unit testing, maybe to detect implementation bugs in optimizations?
Yeah, that might be possible. I think there is some research being done on that. I don't think it's very mature yet, but yeah, who knows? Machine learning is used for a lot of things, so it can also be used for optimization testing in the end.
Yeah, and in this similar direction, I would like to mention that Samiran mentioned, I guess, a paper on the chat, maybe related to this. Yeah. So the next question is from Rohit. Hi, Samiran, you want to ask something?
No, I saw the paper. It looked interesting.
Yeah. So next question is from Rohit. Hi Rohit, I'm glad that you're here. So do you want to ask yourself, or I can ask this for you?
Yeah, let me go. Hi guys, this is Rohit Sharma. So my question is, anyone here working on the optimizations for deep learning accelerator? So like, there are a lot of accelerator companies, right? I mean, including some large corporations and, over 200 smaller startups in the last 2 years alone. And all of them are building some kind of compiler, right? Now, the first higher level stuff is to take the network and compile it to the operators, essentially intermediate code generation, right? And then it goes down and lowered to LLVM. Now, my question really is there any scope or any techniques or any usefulness of those optimizations you have seen at the lower level LLVM optimizations?
So I think this question is more for everyone in general and not specifically for me. So if anyone knows something, please speak.
Anyone working on deep learning accelerator, building a compiler for deep learning accelerator?
I guess I'll assume the silence to be a no.